40 Days of Chemistry, Part 21, this time back to shipwrecks, corrosion and conservation, looking at 9.6.1 electrochemistry. And the first part of this is just a recap of what electrochemistry requires. Electrochemistry is concerned with electron transfer reactions, i.e. redox reactions, and oil rig applies, oxidation is loss, reduction is gain. And redox, don't forget, means reduction-oxidation reactions, which means that one species must be oxidized. It's called the reductant because it causes something else to be reduced, and it's oxidized by losing electrons. Another species is reduced. It's called the oxidant because it causes something else to be oxidized, and being reduced, it means it gains electrons. And thus, there needs to be electron transfer from reductant to oxidant for redox reactions to take place, or for electron transfer reactions to take place. And there needs to be ion transport, and the reason there needs to be ion transport is to maintain charge neutrality and allow the electron transfer to continue. And thus, for electron transfer reactions, you need four things. You need the oxidant, you need a reductant, you need a conductive path for electron transfer, and you also need an electrolyte for ion transfer. They're the four things we need for any electron transfer reaction. And we looked at, the next thing was the ocean as an electrolyte, and there was two reasons we need to know why the ocean is an electrolyte. It's an electrolyte because it contains dissolved salts, but where do those salts come from? And one way that dissolved salts get into the ocean is something called leaching from terrestrial environments. That means that ions are leached or dissolved from terrestrial environments by rainwater, and acid rain, as we know, accelerates that process. The other source of ions in the ocean is from hydrothermal vents at mid-ocean ridges. Now, at mid-ocean ridges, the crust is separating because of tectonic forces, and that causes the crust to crack, allowing water to penetrate into the crust. And the water then goes down and gets heated up, and ions dissolve in that water that seeps into the fissures as it's heated in the crust, and this ion-enriched water is then returned to the ocean via hydrothermal vents, and that water comes out with a very high concentration of ions. A lot of those ions precipitate immediately as they hit the cold water, but many more stay in solution. So they're the two sources of ions in the ocean. The next thing we looked at in this focus area was the history of electrochemistry, and the first science looked at was Galvani. And Galvani, he was doing experiments with static electricity on frogs, and he knew that static electricity caused frogs' legs to jump. But then he observed that when he was doing an experiment with a brass hook and an iron scalpel both touching a frog's nerve in its leg, the frog leg would twitch even though there was no external power supply or no external electricity source. That led him to conclude the electricity must have been generated in the muscle, i.e. there was something called animal electricity. And his contribution to electron transfer reactions were he had the first, even though it was accidental, observation of continuous current flow. He was the first person to understand the physiological effects of electricity in nerves. He got the idea wrong that the muscles generate electricity, but we do know now that nerves do conduct electricity, and that led to the idea or the concept of the branch of science called electrophysiology. But one of the main inspirations, or the main reasons why he contributed to electron transfer reaction, was that he inspired further research by other scientists, particularly Volta, who disagreed with his findings. Now, Volta disagreed with Galvani's conclusions about animal electricity, and he developed something called the voltaic pile to demonstrate it was just similar metals in contact which produce electricity. And his first voltaic pile consisted of copper and zinc discs separated by a brine and acid-soaked cardboard, which acts as the electrolyte, and this pile produced a continuous current. So how did he contribute to electron transfer reactions? Well, first of all, he improved upon Galvani's theory by demonstrating that animal electricity model was not correct. You did not need the animal to produce electricity. He had the first practical and intentional production of a continuous current, and his voltaic pile led to all modern battery technologies as a pretty serious advance in far as electron transfer reactions are concerned. He recognized that different metal combinations produce different currents. I think he ended up using zinc and silver voltaic piles because they produced a bigger current, and that led to the start of the activity series. And one of the other contributions was that his voltaic pile could then be used by other scientists to further understanding by doing more experiments, and one of those scientists was Davy. Now, Humphrey Davy, he developed Volta's pile to produce larger voltages and currents. He then used his voltaic pile to electrolyze molten salts, and he was the first person to discover reactive metals such as sodium and potassium by doing this, and it's because they were reduced back to the metal from their ion form. They were reduced back to the solid metal at the cathode. And there's a picture of his electrochemical cell, or his electrolytic cell, that he used to produce potassium for the first time. So what was his contribution to electron transfer reactions? First of all, he demonstrated a new and practical application of the voltaic pile and electrochemistry in general, and that application was electrolysis, which could be used to extract metals. He also recognized that current produced in the pile wasn't due to the contact between metals, but there must have been some reaction taking place between the metal and electrolyte. He recognized also that if electricity could decompose compounds, as he showed in electrolysis, that chemical bonding must be electrical in nature. So he made some significant contributions to electron transfer reactions, particularly that we could apply them in different ways. And he also inspired Faraday to quantify the process of electrolysis, and Faraday was his assistant, and Faraday continued his research. So here we go. Faraday was Davy's assistant and continued research into electrolytic cells. He developed a device called a coulometer, which enabled him to determine the quantity of charge that passed through an electrolytic cell by measuring the amount of gas produced from a platinum sulfuric acid electrode. So he had this special electrode devised, which consisted of platinum inside sulfuric acid. As the sulfuric acid was electrolyzed, he could measure the gas produced, whether it was hydrogen or oxygen gas being produced, to figure out how much electricity had passed through the cell. And from his research, he was able then to develop quantitative laws of electrolysis that allowed electrolytic techniques to be applied to industrial and scientific processes. And the first law was the mass of a substance altered, which means deposited or dissolved, whichever one, at electrode, is directly proportional to the quantity of electricity passing through the cell. And the second one, the mass of an element altered, once again that means either dissolved or produced at an electrode, is proportional to its effective weight. And the effective weight is the atomic weight to valency ratio. And the last thing Faraday contributed to electron transfer reactions, apart from quantifying them for us, was that he contributed the terminology we use to describe electrochemical reactions or electrochemical cells, and thus enabling scientists to communicate their understanding of electron transfer reactions. Some of those terminology, for example, were anode, cathode, electrolyte, etc., etc., etc. So that's the end of focus area 9.6.1. The next one will be 9.6.2, steels and rusting.